Jnanam paramam dhyayam. Knowledge is supreme.
In the last lecture, we derived the mole balance for internal diffusion with surface reaction simultaneously happening. We will build upon that today and solve the equation, and we will look at how the concentration profile actually is a function of the position and what insights we can derive from the concentration profile. So, if we take a catalyst pellet where we have species A which is diffusing from bulk, if the concentration of the species at the surface is CAS and there is internal diffusion that is happening of the species, we derived the mole balance in the last class where we said that the mole balance is d square Ca by dr square plus 2 by r into dCA by dr minus Kn into Ca to the power of n divided by dE equal to 0 for a nth order reaction, where Kn takes care of the surface area which is available for the reaction, density of catalyst, so on and so forth, and the boundary conditions being Ca equal to Cas at r equal to capital R, where capital R is the radius of the pellet that we considered and Ca is finite at r equal to 0. So, what we will do now is we will solve this equation and then we will find out what is Ca versus r and what kind of insights we can get about the diffusion process by looking at the profile of concentration versus position inside the pellet. So, as a first step, what we will do is we will actually non-dimensionalize the model equation, and it is often useful to actually non-dimensionalize the equation so that the solution and the insights we get can actually be independent of the size of the pellet that we consider. So, let us first non-dimensionalize the equation, and it also helps in solving the model equation. Let us assume that psi is Ca, which is the local concentration at any position r, divided by the surface concentration Cas. So, what will be the range for this value psi? Because Cas is the concentration of the species that comes from the surface into the catalyst pellet. Therefore, the maximum possible concentration anywhere inside the pellet can at best be the surface concentration itself. So, therefore, psi is essentially going to be between 0 and 1. So, clearly psi is always in the range of between 0 and 1, 0 when the concentration is 0 at any location, when 1 when the concentration is equal to that of the surface concentration. Let us also define the non-dimensional quantity for position, because the model equation has both concentration and position. Let us define this as r by capital R. What will be the range for the lambda, which is the dimensionless position? Once again, clearly lambda is always between 0 and 1. So, let us first look at the boundary conditions in this non-dimensional form. So, the first boundary condition is Ca equal to Cas at r is equal to capital R. So, this means that in the non-dimensional form we will see that psi equal to Ca by Cas, which should be equal to 1 at lambda equal to r by r equal to 1. So, the boundary condition is that psi equal to 1 at lambda equal to 1. This is the boundary condition, one of the boundary conditions in the non-dimensional variables that we have just defined. And what will be the second boundary condition? The second boundary condition will essentially be psi is finite at r equal to 0 or lambda equal to 0. So, concentration Ca is finite, which implies that psi is finite at r equal to 0 or r lambda, which is the dimensionless position, that equal to 0. So, now let us look at the model equations. Let us try to find the dimensionless form of the model equation. So, the model equation has the second derivative of concentration with position, it has first derivative of concentration with position. So, let us try to find out what is the first derivative dCA by dr in terms of the dimensionless quantities. Now, simply by chain rule we can write this as dCA by d lambda into d lambda by dr, and from here we can rewrite this as by dr is essentially equal to d psi by d lambda multiplied by dCA by d psi into d lambda by dr. Now, we know that psi is equal to Ca by Cas. So, from here dCA by d psi is essentially equal to Cas, and we know that lambda is equal to r by capital R. So, from here d lambda by dr is essentially equal to 1 by r. So, substituting these, we will find that dCA by dr is equal to 1 by r into Cas into d psi by d lambda. Okay. So, that is equal to Cas by r into d psi by d lambda. So, now if we now look at the dimensionless form for the second derivative or second derivative in the new variables, d square Ca by dr square, that is nothing but d by dr into dCA by dr, but we just found out what is dCA by dr. So, that should be equal to d by dr into Cas by r into d psi by d lambda, and this we can write by chain rule as d by d lambda into Cas by r d psi by d lambda into d lambda by dr, which is equal to Cas by r square into d square psi by d lambda square. So, now we can plug in the first derivative and second derivative in terms of the new variables, whatever new variables we have just defined, that we can substitute into the model equation, and we can find out the model equation in the new variables. So, what is the model equation? The model equation is d square Ca by dr square plus 2 by r dCA by dr minus Kn Ca to the power of n divided by d equal to 0. So, we know that d square Ca by dr square is nothing but Cas by r square into d square Ca by d lambda square, plus we have 2 by, we can write r in terms of lambda, which is r lambda into capital R is small r, and that multiplied by Cas by r into d psi a, this should be psi a, d psi by d lambda minus Kn into Ca to the power of n equal to 0 divided by dE. So therefore, we can rewrite this expression as d square psi by d lambda square plus 2 by lambda into d psi by d lambda minus Kn r square divided by dE into Cas, and we can also now write Can in terms of the new variable. So that will be Cas to the power of n into psi to the power of n equal to 0. So this we can rewrite as d square psi by d lambda square minus 2 by lambda d psi by d lambda, that should be plus, minus Kn r square by dE into Cas to the power of n minus 1 into psi to the power of n equal to 0. So this is the model equation in the dimensionless form, which incorporates the dimensionless quantities we just defined. So now if you stare at this expression here, in the model equation, the dimensionless form, where we have Kn r square by dE and Cas to the power of n minus 1. So now let us see what this coefficient actually means. So the coefficient in front of psi n term, which is the rate term here, is essentially called as the Thiele modulus, square of the Thiele modulus. So we can define phi n square as Kn r square Cas to the power of n minus 1 divided by dE. So now this expression here is what is famously called as the square of the Thiele modulus, where the Thiele modulus phi n is given by square root of Kn r square Cas to the power of n minus 1 divided by dE. So if we stare at this expression here, what we see is that in the numerator we have the rate constant, or which signifies the rate at which the reaction happens, and in the denominator we have effective diffusivity. So now we usually use this notation of phi subscript n, because we use phi typically for porosity. So we use phi subscript n to actually refer to Thiele modulus for catalytic systems. We can now rewrite the phi square expression here in a slightly different manner. We can rewrite this expression as phi n square is equal to Kn into r multiplied by Cas to the power of n divided by dE into Cas minus 0 divided by r. So this quantity here in the numerator, refers to the surface reaction rate, and the quantity in the denominator actually refers to the diffusion rate of the species. So one can actually look at Thiele modulus as a ratio of the surface reaction rate to the diffusion rate of the species. Now what happens if phi square is very large? So if phi square is very large, it means that the diffusion of the species is very small. So if diffusion of species is very small, then one can actually think of the possibility that the overall reaction rate is essentially controlled by the diffusion of the species, or diffusion rate may be the slowest step in the whole process. So now let us consider the two cases where phi square is phi n square is large and phi n square is actually small. So, if phi n square is large, then it means that the diffusion rate of the species is very, very small, and therefore, if phi n square is large, it means that the diffusion rate is small, which implies that the internal diffusion is controlling the overall reaction rate. Suppose if phi n square is small, then it means that the surface reaction might be controlling the overall rate. So, if one knows what is the Thiele modulus for a given system that we are looking at, given catalytic reaction and the reaction that is happening, then based on Thiele modulus, value of Thiele modulus, one can actually find out whether the reaction is likely to be internal diffusion controlled or it is likely to be the surface reaction controlled. Suppose we take a first order case, first order reaction case. Let us consider the Suppose let us consider first order reaction. Let us consider first order reaction here, where now order of the reaction n is essentially equal to 1, and the model equation in the dimensionless form is essentially d square psi by dr square, d lambda square plus 2 by lambda d psi by d lambda minus phi 1 square into psi equal to 0, and the boundary conditions are essentially psi equal to 1 at lambda equal to 1 and psi is finite at lambda equal to 0. So, what will be the expression for phi 1 square? So, phi 1 square will be k1, which will be the rate constant for the first order reaction, multiplied by r square into CAS to the power of n minus 1, but n is 1. So, therefore, CAS to the power of n minus 1, that is essentially equal to 0 divided by the effective diffusivity, which is essentially equal to k1 r square by d. So, now Thiele modulus now is essentially square root of this expression. So, phi 1 is essentially equal to k1 r square by d, which can be, so I can now pull out r from here. So, that is r into square root of k1 by d. So, what are the units of phi 1? So, let us look at the units of phi 1. Units of r is, let us say, meter. If I use SI units, units of r is meter. What will be the units of rate constant k1 for a first order reaction? It is second inverse. And what are the units of effective diffusivity? Is meter square second inverse. So, if I now substitute this into the expression for Thiele modulus, I can see that the units of phi 1 is radius is given by meter, and square root of the units for rate constant is second minus 1, and the units for diffusivity is meter square second minus 1. So, essentially you will see that the dimensions of Thiele modulus is actually no dimension, it is a dimensionless quantity. So, it is a dimensionless quantity which actually looks at the ratio of surface reaction to the diffusion rate, or it actually captures the relative effects of surface reaction and the surface reaction rate and the diffusion rate. It is a quantitative number which helps in identifying whether the surface reaction rate is dominating or the diffusion rate is actually dominating. So, how to solve this equation? So, how do we solve this model? So, in order to solve the model, we need to make a simple substitution. So, let us introduce a substitution where we define a quantity called y, which is essentially equal to psi times lambda. So, from here we can see that dy, we can find out dy by d psi. We can also, of course, we can find out d psi by dy, but what we require is actually d psi by d lambda. So, how do we find d psi by d lambda? So, let us rewrite this expression as psi is equal to y by lambda, and so now d psi by d lambda is essentially given by 1 by lambda into dy by d lambda minus y by lambda square. What is next? We need to find out what is d square psi by d lambda square. So, let us find out what that is. So, d square psi by d lambda square is essentially given by d by d lambda of d psi by d lambda, and that is equal to d by d lambda of, we already know what is d psi by d lambda, we just found out what is d psi by d lambda. So, we substitute that here. So, that will be 1 by lambda dy by d lambda minus y by lambda square. That is equal to 1 by lambda d square y by d lambda square minus 1 by lambda square dy by d lambda minus 1 by lambda square into dy by d lambda plus 2y by lambda cube. So, now we can, so this is equal to 1 by lambda d square y by d lambda square minus 2 by lambda square lambda plus 2y by lambda cube. So, we know what is the second derivative, we also know what is the first derivative, and we can now substitute that into the model equation. Let us do that. So, what is the model equation? The model equation is d square psi by d lambda square plus 2 by lambda d psi by d lambda minus phi 1 square into psi equal to 0. So, from this expression we can substitute d square psi by d lambda square, and so that is essentially equal to 1 by lambda d square y by d lambda square minus 2 by lambda square dy by d lambda plus 2y by lambda cube, and now we need to substitute for the first derivative. So, that will be 2 by lambda into 1 by lambda dy by d lambda minus y by lambda square and minus phi 1 square. Psi is essentially given by y divided by lambda. So, that is equal to 0. So, from here we can see that this term cancels out with this term and this term cancels out with this term, and so essentially the model equation is 1 by lambda d square y by d lambda square minus phi 1 square into y by lambda equal to 0, which essentially means that the model equation is reduced to d square y by d lambda square minus phi 1 square y equal to 0. So, what we have seen in today's lecture is we started from the model equation that we derived in the previous lecture, and then we non-dimensionalized the equation. We found out what is the Thiele modulus, the dimensionless quantity which characterizes the ratio of or captures the ratio of surface reaction rate to diffusion rate. And then we introduce the transformation of y equal to psi lambda, which is required to solve the model that we are looking at. In the next lecture, we will actually solve the model and we will see what the profile of concentration with respect to position and what is the kind of insights that we can obtain from the solution of the model equation. Thank you.